Hi, welcome back. Today I'm going to, or in this short video, about 30 minutes maybe, I want to do a couple, maybe three problems from the end of chapter of this impulse and momentum. So let's get to it. So you have a 200-gram bullet, or ball, sorry, is dropped from a height of 2 meters. So let's see, so the ball is dropped from here, 2 meters, dropped from rest basically. So you go like this, you drop the ball, so the ball comes in, it will hit the floor, and it will have a certain velocity here, let's call it V initial when it hits the floor, and then it will bounce back, and then it will have some velocity here, let's call it V final after hitting the floor, and then it goes up, but it doesn't get as high. Just from experience, if you let a ball bounce, it will not bounce as high because it loses some kinetic energy due to inelastic or frictional forces. It only bounces up to a height of 5 meters. It says here the figure shows the impulse received from the floor. So when it hits the floor, the ball applies the force of the floor, so the floor applies a force on the ball. That's the normal force. And that normal force is variable. So they're modeling it to change like this. So as the ball hits the floor, the force increases and increases until it reaches a peak. And then when it's leaving the floor, the force will decrease until it becomes 0. And obviously when the ball is no longer touching the floor, the force is 0. And the time here is 4 milliseconds. So that's 4 times 10 to the minus 3 seconds. As you experience, I mean, when a ball hits the floor, it's in contact with the floor for a very short time, milliseconds. And the question is, what's this F max? Well, we know from Newton's second law that F is dp dt, where p is the momentum, and so F dt integral is equal to the change in momentum, and this is this area. Right? The integral will be the area under the curve of this force versus time. And the change in momentum is the final momentum minus the initial momentum. So that's momentum, remember, is mass times velocity. So mv final minus mv initial. The left side here would be the area of this curve. And the area, well, this integral will depend on exact shape of this function. In this case, it's a triangle, so the area is half the base times the height. Half the base is half of the 4 milliseconds times the height. So the area would be 1/2. The base is 4 milliseconds, so that's 4 times 10 to the minus 3, and then times F max, that is the height. So if I find this, V final, V initial, and then I have this left side, I can just find F max. So let's find what the velocity is when it hits the floor, when it's coming to hit the floor, right before hitting, and then right after hitting the floor, what would it be? Well, let's call this here the height here, h1, and the height here is h2. And then we know from kinematics that when you drop something that the velocity initially is 0, and then what's the velocity at the bottom? I'm calling it V initial, and it is equal to, you can use kinematics or you can use conservation of energy if you like. Energy here is mgh, the energy at the bottom is 1/2 mv squared. Let me use conservation of energy. So 1/2 mv initial squared is equal to mgh h1, and therefore v initial will be 2g h1 square root, and I will take the negative sign because it's coming down. When it leaves as it's going up, again I will relate the velocity here to the maximum height here, and I would come up with the fact that v final would be 2g h2 square root, and it would be positive because this one is leaving the floor, going upward, And let's call, yeah, that's the positive direction. It'll be the positive y direction. Okay, so at this moment you could just substitute, but I will just, right now, mv final minus mv initial, so delta p will be mv final minus mv initial, so that's, I would factor the m out, so m times what? V final is square root of 2gh, h2, and then V initial is, so minus, and then V initial itself is negative the square root of 2gh1. So minus minus, that's a plus, so you have delta P will be m, and then the square root of 2gh can be factored out, so you have the square root, I'm sorry, the square root of just 2g. And then here I will just have the square root of h2 minus the square root of h1. Again, this may not be necessary. You can just solve, you can just find delta p. You could just find it numerically. And now we'll find f max. So f max will be this delta p divided by this number here, by 1/2 of 4 times 10 to the minus 3. So let's see. So f max will be this delta p, which is m2g the square root of h2. Oh, I'm sorry. This is minus minus, so it's a plus. Yeah, plus. Yeah, plus here. Square root of h1 divided by this number here, which is 1/2 of 4 times 10 to the minus 3. 1/2 of 4 times 10 to the minus 3. Now you can substitute the numbers. The mass is, it's a 200 gram ball, so 2 times 10 to the minus 3, so 2 times 10 to the minus 3, that's the mass of the ball. And then the square root of 2 times 9.8 for G. And then H2 was 1.5, so square root of 1.5 plus the square root of 2 for H1. H1 was 2 meters. H2 was 1.5. And then you divide here by 1/2 of 4 is 2. 2 times 10 to the minus 3. 10 to the minus 3 cancels. Oh, and then, oh, this should say 200 times 10 to the minus 3. Another mistake. Glad I caught it. 200. And so we find that f max. Let me plug in the numbers. Plug in the numbers. So you would have, I'll start with those square roots. 1.5 square root plus the square root of 2. Okay, and then times the square root of 2 times 9.8. Should say close parentheses here. And then times 200 over 2, which is 100. So times 100. I have 1168, but let me just double check my algebra here. Let's see. Okay, I thought I made a mistake, but I actually didn't. Just the book has here 5 milliseconds instead of 4. So this is 5. Let me just stick with their problem. So this should say 5 here instead of 4. This should say 5. 1/2 of 5 is 2.5. So 2.5. So when you multiply through, you get 935. 35 units. Approximately 900 something newtons. Yeah, that looks good. Now, let's look at the next problem. We'll read it together, and then I want to do some bookkeeping work, and then and then we'll actually get to the problem itself. So let's read it. It says, a block of mass m slides along a frictionless track with speed Vm. It collides with a stationary block of mass capital M. Find an expression for the minimum value, not from, for the minimum value of Vm that will allow the second block to circle the loop without falling off. If the collision is perfectly inelastic, and then if the collision is perfectly elastic. So these two blocks, let's do the first case here. If it's inelastic, so this block hits this block, they stick together. Then they come and then circle and then come back. And we would like them to make the full circle. So when they are here, what should their speed be here so that they don't fall off? They don't lose contact with the floor. So let me remind you of the loop problem. How it works. So if you have a like this is the radius r. So let's say the mass here is m, right? You have a mass m here. And it starts here with some speed v, v initial. Let me call it v initial. And it's circling. So what should the speed here be? Well, when it's at this point here, there are two forces on it. There is gravity pulling it down, mg, and then there is the normal force from the top, and normal force like that. So these two forces are on it, and it will lose contact. And let's write Newton's second law. Let's say this is the negative y direction, so I have mg in the downward direction, minus the normal force that's in the downward direction. And since this is circular motion, this is equal to mv squared over r, and this acceleration is also in the downward direction, so that's negative. So everything is basically positive. So you get mg plus the normal force equals to mv squared over r. Now, it will lose contact if the normal force approaches zero. So let's make it minimum. So if v is large, the normal force is fine. It will be larger than zero. But if it's below a certain number, the normal force will become zero. And I want to find that minimum value for which the normal force is equal to zero. So if you take the limit as you approach the normal force from the right, as it approaches zero, then just plug in zero here, so you get normal force going to zero. We get mg is equal to mv squared over r, and so v will equal to gr square root. That's the speed, that's the minimum speed needed here. So what speed do you need here? Well, then you can use conservation of energy. In here, it's all kinetic. In here, you have some potential and some kinetic. And if this is radius r, then the height, this height, is 2r. So the total mechanical energy is just kinetic, so you have 1/2 mv initial squared. It's equal to the total mechanical energy here, which is, some of it is kinetic, which is 1/2 mv squared, which is v is the speed here, and then plus mgh, and so the mass simply cancels, and I want to know what v initial is. So I can multiply both sides by 2, so I get v initial squared is equal to v squared plus 2gh. And so what's v squared? Well, v is gr, so when you square the g and the r, you get, when you square this square root, you just get gr for v squared, and then plus 2gh. But what's the height? The height is 2r. Sorry, I should say 2r. So it's 2r. And so I get v initial squared will equal to what? 2 times 2 is 4, and then you get a 4 here, so you have, you have 5 GR. And so the initial, at minimum, the speed with which this mass has to move at the bottom should be 5 GR square root. That's the minimum speed needed at the bottom. So it's the square root of 5 GR. So let's go here, go back to the original problem here. So remember, the initial should be 5 square root of 5 GR. So now we will do it into steps here. So suppose the collision is inelastic, so these two will collide. So we will do that first case, inelastic. Oh, I need chalk. This is chalkboard. So for case A, inelastic. So I will use conservation of momentum because inelastic momentum is conserved. So this one has momentum, so mvm is the initial momentum. mvm should equal to the final momentum, but the final momentum is these two hit each other and they become a larger mass, little m plus capital M moving at some v. I will call it v initial. That's the v after the collision. So the momentum afterwards will be m plus capital M v naught. So that's that. So Vm will equal to little m plus capital M V naught divided by little m. But what is this minimum V naught here? What should it be? What should their speed after the collision be so that it will make it through? Well, it should be the square root of 5 GR. So Vm should be square root of 5 GR here, and then little m plus capital M divided by little m. That's the minimum speed needed. So little m needs to be coming in before collision with this speed. That's related to the masses. So if you give me the masses and the radius, I will tell you what that minimum speed is. So that it has to be coming with this speed, so that when it collides, it ends up with this speed, and that speed is needed to come around and make it. Now, what if the collision is elastic? What if the collision is elastic? So part B. Well, we know that for an elastic collision, you have m here, and you have capital M here. This is before. This one is coming in with some speed Vm. This one has speed 0. After the collision, you will have little m here, and it has speed Vm prime. And this one will have some speed, I would call it V initial. And we have formulas for those. We use conservation of energy and conservation of momentum to derive them. I will write them down on the board. Actually, let me draw it the way we learned about it in lecture and then do it for this particular situation. I will label this one as M1, this one is M2, and then so it just corresponds to what we learned. If it's elastic, and let's say you have M1 here coming in with speed V1 initial, and this is M2. M2 is not moving, so afterwards you would have M1 with some speed V1 final, and M2 with some speed V2 final. I think this is the notation, but let me double check. Yes, that's correct. So this speed, the speeds are as follows. V1 final after the collision will be M1 minus M2 over M1 plus M2 times V1 initial, and V2 final, V2 after the collision will be twice M2, I believe, over M1 plus M2 V1 initial. Let me just double check this one. It's not a formula. Yeah, it's not a formula I remember at all times. Yeah, this happens to be M1. You can derive it if needed, or you can just look it up. So that's the formula that happens to be. So which one is more relevant? Well, we would like this capital M to make it around. So after the collision, capital M needs to have this speed. This is the capital M. So it needs to have this to be V initial. So we get V initial needs to equal to this. To little M1 is little m, and then little m for M1, and then capital M for this one, times V1 initial, and V1 initial we're calling Vm. And we would like V initial to be how much? Square root of 5gr. And well, we can solve for Vm from this. So you get Vm will be little m plus capital M times 5gr square root divided by twice m. And you can compare them. All right, so this last question here, it says a 20 kilogram wood block hangs from a 2 meter long wire. The maximum tension the wire can withstand without breaking is 400 newtons. So let's draw the first part here. So here is the wooden block. This is 2 meters. And let me call this the mass of the wooden block, M block. And it's 20 kilograms. Well, obviously it didn't break, so the tension better not be 400. You have mg downward, which is about 9.8 times 20. That's approximately 200 newtons. So the tension needed to keep it hanging is 200 newtons, about 200 newtons. So that's fine, it didn't break. Now, a 1 kilogram projectile traveling horizontally hits and embeds itself into this. So here's the projectile, let me call it MP for projectile. Comes in with some speed, V initial. So it hits this and embeds itself into it. So what happens? So, well, they become one projectile plus the mass of the block. They become one big mass, and they will be moving at some speed this way. And as you can see, it will be circular motion because they will go like this. They will follow this arc, right, like that. And the question is, what should the maximum speed be so that the tension barely holds, the wire barely holds? So basically, the tension will be 400 newtons. What speed should it be so that the tension is 400 newtons? Well, first of all, let's use conservation of momentum to figure out the speed right before and right after the collision. It's inelastic, so that should be fairly simple. So it's inelastic, so the momentum before is the mass of the projectile times V initial, and that should equal to the momentum after. Both are stuck together, so it would move at the same speed. So the mass of the projectile plus the block, that's the total mass, times the speed after the collision. And therefore, the speed after the collision, V, will be the mass of the projectile, V initial, divided by the mass of the projectile plus the mass of the block. I will substitute the numbers in a moment. Now, they're moving at this speed in a circle. So what are the forces? Well, you still have the tension upward, you have mg downward, and you must have, since it's circular motion, you have to accelerate toward the center with an acceleration, equal to v squared over r. And r is the length. So use now the second law. This is after the collision. We got the net force, tension minus mg. This is positive direction, plus y. So the tension minus mg, what is m? Well, m is the mass of the projectile plus the mass of the block. Tension minus mg, the mass of the projectile plus the mass of the block, times gravity. That's tension minus mg. That has to equal to the mass times acceleration. The mass times the acceleration. The mass, again, is the projectile plus the block, times the acceleration. The acceleration is v squared over r. V squared divided by r. But v is this. Okay? So we will say then the tension minus mp plus mb times gravity is equal to mp plus mb, and then v squared. We have to square this. So that would be mp over mp plus mb squared, and then v initial squared. Oh, and don't forget the over r. I think we can just now cancel one of these, and then just substitute the numbers. We can substitute the numbers and solve for v. We want the tension to be as large as possible, so that's 400 minus the mass of the projectile is 1 kilogram. The mass of the block is 20 kilograms. G, of course, 9.8 equals to the mass of the projectile is 1, so that's 1 squared over the r is the length here, which is 2 meters. The length of the bar is 2 meters. 2. So I took care of this, and I need to take care of this one. The mass of the projectile again is 1, the block is 20, and then v initial squared. So we need to find what v initial is. So subtract these first. So let me get my calculator here. So let me get, so 400 minus 21 times 9.8, 21 times 9.8. That gives me 194.2. Let's write it down. So 194.2 equals to, and here I have 1 over 2 times 21 is 42 v squared. So v will be 42 times this, oh, and then you square root it. So times 42. Then we need to square root it. And I get 90.3 meters, about 90 meters per second. And that should be it. All right. All right, so enjoy the rest of the problems, and I will see you when we start rotational motion next. So what's coming up is the next unit will be rotational motion, Newton's universal law of gravitation, and then fluids. That's the next unit. And then the following unit will be oscillations, waves, and sound.